people are still coming in, but we need to start since we have a pretty tight agenda today. Folks, welcome to the Apache Sedona Community Office Hour of October. Today, we're going to have a special event. As many of you probably already know, so about 2 weeks ago, we announced 2 new sub-projects of Apache Sedona, SedonaDB and SpatialBench. Today, we're going to talk about that. So here is the agenda today, right? So first, we're going to talk about Apache Sedona 1.8, so which is the latest major release we made about 3 weeks ago. And then we can also give a brief intro of SedonaDB and SpatialBench by myself. And then I'm going to hand the mic over to Dewey, Christine, Feng, Pranav, and James. So they're going to talk about and give you a demo about different components of SedonaDB. And also, we can also talk about the design of SpatialBench, as well as how the data gets generated and how did we perform the first version of the SpatialBench benchmark result. And while we're giving the presentation, the audience, please feel free to raise your hand, feel free to post your questions in Q&A, right? We're happy to take any questions. All right, let's move on. So many of you probably have used Sedona before, but just give you a quick recap about what Sedona is, or Apache Sedona is. So Apache Sedona is the most popular open source cluster computing engine for big geospatial data. So it is Apache top level project. We have our website at sedona.apache.org, and our GitHub is also under the Apache Software Foundation. We have our social media account on X and on LinkedIn. So please be sure to follow us on social media to get the latest updates from the community. Sedona has been a very popular project. As you can see from the logos here, Sedona is being widely used by many companies across the industry. That includes, JB Hunt, T-Mobile, Allstate, Landos Lake, Leaf, Amazon, right? Many companies use Sedona in production. And its monthly downloads has exceeded 2 million. And the overall downloads of Sedona has exceeded 50 million. And I think right now it is sort of close to 60 million. And its download has 200% growth year to year. If you look at our GitHub right now, we have over 140 contributors. So if you're interested, please be sure to join the community and start to contribute. Here is a brief overview about the Sedona ecosystem, right? So Sedona basically have multiple layers. The top layer is what we call spatial query processing layer. But this layer has different language binding. You can interact with Apache Sedona through Spatial SQL, Python, Java, and R. And you can also connect Sedona to different developer tools, including Apache Zeppelin, Tableau, Jupyter Notebook. You can also connect them to GeoPandas and RStudio. And this query processing layer also take a spatial query as input, and then it automatically decides the best spatial query algorithm to run this query in a compute cluster on hundreds of machines. This query optimizer can consider the data statistics of the input data and choose the best algorithm for this particular query. The second layer is what we call distributed spatial dataset layer. So in this layer, it basically decides how the spatial data is laid out in the cluster. We have what we call distributed spatial data partition that partitions spatial data based on their spatial proximity and also load balance. We also have distributed spatial indexing that builds index on different partitions of the input data. We also have spatial data serializer as well. And Sedona actually runs on top of a number of different distributed engines. So it runs on Apache Spark for batch processing. It runs on Apache Flink for stream processing. It also runs on Snowflake for batch processing. By far, our support on Spark is the most comprehensive one. It also supports many different data formats, including GeoJSON, GeoParquet, Parquet, and GeoTIFF, many other raster datasets as well. And Sedona follows the 3-month release cadence. So we made a couple releases this year, right? So the latest release we had for Sedona is 1.8 that was made on September 12th. In this Sedona 1.8, there are lots of exciting features. So we have covered many of these topics in the past few months throughout the different community office hour. So one of the most important thing is the Java 11, Java 17 support. We basically dropped Java 8 in the latest release of Sedona. And we also introduced Spark 4.0 support. That means you now can run Sedona on Spark 4.0 on AWS EMR, on other cloud as well. We also introduced PyFlink support. You'll be able to run Sedona and Flink in a Python environment. We also have more accurate ST transform, as well as some geography operators. And one of the most exciting features in the 1.8 release is the GeoPandas API on Sedona. That means if you have a GeoPandas program right now, you can actually change one line of import, and that program will actually run on top of Sedona, right? Actually, that basically allows you to migrate a GeoPandas program to Sedona. And if you have small data, you can stick to GeoPandas. But if you want to have better scalability on large scale data set, then you can try to use GeoPandas API on Sedona. So that's about Sedona 1.8. Now, we're so excited to announce the 2 new Apache Sedona sub-projects, SedonaDB and the SpatialBench. SedonaDB is a single-node analytics database engine with geospatial as a first-class citizen. And the SpatialBench is a benchmark for assessing geospatial SQL analytics query performance across different database systems. Now, let's take a quick look at SedonaDB. As you already know, Sedona worked with large-scale data in the past, right? Worked with Spark, with Flink, with Snowflake, right? But there was a problem is that that Sedona is a little bit hard to install, right? You always need to find a cloud vendor, find a cloud environment to install Sedona there, and you need to be able to run clusters, hundreds of machines. And oftentimes the performance of Sedona is not great on single machine, on your laptop, on small data set. Now, since we introduced the SedonaDB, right? SedonaDB is gonna fill in the gap here. It's gonna work great on small data set and on your laptop. By having SedonaDB, we finally make Sedona complete. Sedona now, it is an engine that makes it easy for processing geospatial data sets at any scale. So here is a brief overview of SedonaDB. SedonaDB is written in Rust, but it's providing bindings for Python and R, and of course, spatial SQL. And by nature, it uses columnar in-memory datasets. It is fully compatible with Apache Arrow. That means there is 0 copy involved in SedonaDB. And we have spatial query optimization that performs heuristic-based and cost-based optimization on spatial queries, in particular, very complicated spatial queries and spatial joins. And for spatial query processing, we have lots of query operators, including spatial join, k-nearest neighbor join, spatial filtering, right? And we are actively working on the spatial raster functions, and the raster function support going to coming soon, and they're going to be out in a few months. And we expect raster functions of SedonaDB is on par with what we already have in Apache Sedona. SpatialBench. So why we develop SpatialBench? So when we developed SedonaDB in the past few months, we noticed that we actually need a benchmark to systematically evaluate the performance of SedonaDB, and it needs to be fair and transparent, right? So here are the goals we have when we design SpatialBench. So we want to focus on reproducibility. So basically, anybody that has the access to the SpatialBench GitHub repository they should be able to reproduce the exact same data set by calling the generator. And also they should be able to reproduce a performance using the exact query we provide. And it needs to have systematic coverage. It needs to test vector data, raster data, spatial filters, spatial joins, CRS, and query optimization as well. Not a single query. It needs to be a combination of different spatial operators that represent realistic use cases. We also need to have scalability tests. It needs to support different scale factors from scale factor 1 to 1,000, for example. And it needs to be fair and transparent, right? The benchmark is open source. It is also open. It is under open governance, meaning that it is a party project. If you have any questions or concerns, just go ahead and join the community and contribute, right? So without standards, there can be no improvement for any spatial engines. And there are a couple components involved in SpatialBench, including data model, data generator, queries, and results. But we will cover that later on in the talk today. Here are the initial results we have on SpatialBench. We run SpatialBench actually on couple software, including SedonaDB, DuckDB, and GeoPandas, using scale factor 1 and scale factor 10. As you can see from the two charts here, SedonaDB shows balanced performance on almost all queries, and it is the only engine that can finish SpatialBench scale factor 1 and scale factor 10. And DuckDB has great performance on spatial filters and certain geometric operations, but it is having a hard time running spatial joins and k-nearest neighbor queries. And GeoPandas is widely used in Python. It has great performance on still on filter queries, but it requires manual optimizations and it needs parallelization. Right now, it only works on a single CPU core by default. All right. So now I'm going to hand over the mic to Dewey. So he's going to give you guys a demo about the cool features of SedonaDB. Dewey, please take over.
Yeah, thanks. Yeah, SedonaDB is exciting. And I think the first question that we get every single time is, what is it? Exactly. Even after we explain it, I mean, we know it's fast. We're good at explaining that. But yeah, I think the easiest way to sort of figure out what it is to start typing. So when you're running Sedona, you're working with Sedona Spark. Working with SedonaDB, it's SedonaDB. And just like there's a section in Sedona, there's a section in SedonaDB as well. Connecting is a bit of a misnomer here. We're not really connecting to anything. This is sort of just a handle for all your tables and the local stuff you're creating, the local temporary stuff that you might have, so that it doesn't intersect with somebody else that might use Sedona end up with. Yeah, so you can run SQL. One thing I forgot to do is turn on interactive mode. Just like Spark won't automatically execute something because it might be huge. SedonaDB won't do that either. Yeah, that's good. But I'm particularly proud of this table. The printing of tables is actually quite hard to do. And if you want to take a look at the schema here, then you can have it. Of course, this is like not a very interesting SQL query, and so I will spend a lot of time with it. What you probably want to do is like load some data. And I put together, there's a whole bunch of data here at geoarrow.org. I work in the team geoarrow. And we have a bunch of example data that we use all the time. So I'll put this one here. This one is, I used to live in Nova Scotia, and this is a whole bunch of the water junctions from the hydrometric network. This is a flat GeoBuff file, so we'll need GeoPandas to read it. We don't have a flat GeoBuff reader yet. GeoPandas is pretty good about taking lots of stuff as input. You get there. And SedonaDB can make something out of or create a data frame out of just about anything. This is our GeoPandas data frame, and SedonaDB is scanning it. There's a bit of copying that happens here because GeoPandas doesn't have the exact same memory representation as Sedona, which is Arrow, but it's pretty good. And I haven't been able to make this take any reasonable amount of time. Like, this is always pretty fast for me. So one of the things that we really want to do is like to actually do something with it. Like SedonaDB, we've heard that it's fast and it can do a lot of things. And most of the things right now are exposed via SQL. So how we'll be writing SQL queries. Basically, this is like a PostGIS or a DuckDB spatial SQL query against maybe some data that you've already had. So here we've got the easy one is select all from water, but there's all sorts of things that you could do. Give it every point 100-meter buffer, and you can do that too. And we have great interop, so we can do things like map this using Longboard. So Longboard, if no one's used it, it's a really great interactive mapper, and it has really great automatic settings. So you don't have to think a whole lot about what's going on. So here we have it sort of all coming out here. And I think that it's in a really tiny, oh yeah, there we go. The color is very small. And so here we have our little 100-meter buffer around all of these things. This is a funny data set. I didn't know this before I put it together, but ever since I've done it, I've realized that these are rocks and lakes. Almost 100% is what this data set is. Rocks and lakes. Anyway, that is sort of the gist of what SedonaDB can do. We can send it to all sorts of things. I can send it back to GeoPandas if you want. You can send it back to View. And I'll leave it to Kristen and Feng to demonstrate some of the more exciting things that it can do. But in a nutshell, this is kind of what SedonaDB is all about. It's sort of interacting with your existing Python workflow in a more minimal way. There's no cluster. It's just a Python package, and we're not trying to replace anybody's workflow. We're mostly just trying to like insert ourselves into existing workflow. So that, if that slow GeoPandas join that's happening, or if you are having trouble reading GeoParquet from a massive file store, these are all things that SedonaDB is great at. And we can send it to pandas when you're done, or you can use it as GeoPandas input to whatever you're working on.
Great work, Dewey. Now, Christine, please. Let's talk about spatial join.
Yeah, all right. I also have a demo for spatial join. Now, let me share my screen. Okay, let me share my browser. Okay, can you see my screen?
Yes.
Oh, okay. Now let's talk about spatial joins. I think all you guys attending this meeting may already know what is spatial join, so I will not waste time on introducing what it is. So let's just jump into the demo. This demo is computing the number of coffee shops in each county. And I have already prepared some data set. Now, first, let's just do what Dewey has done, connecting to SedonaDB. And then let's load some data. So you can see that you can use sd.readParquet to read a local directory or directory on S3 or whatever to SedonaDB and name it as a view so that you can use this identifier as the name of a table or relation. And then let's filter the data a little bit to only preserve the counties in California. This is for reducing the size of the data so that we can just accomplish the query very quickly in this demo. So as you can see, you can just use .show or use interactive mode, but here I prefer using show to show this data set explicitly. So you can see that these are just the polygons of the counties. By the way, this data set is the division area from Overture maps. I've downloaded to a local drive because I have poor networking, so connecting to S3 is a little bit of painful for me. Then I decided to load the locations of coffee shops from the places dataset. This is also from Overture maps. And you can also show this dataset or using, for example, as the SQL select star from coffee shop. Oh, what's wrong? Coffee shops, sorry. And there's another feature of SedonaDB that you can look at the query plan. There's a explain method. This is pretty like Spark SQL, PySpark, but explain actually returns a data frame. So you have to show it to return to get the query plan. So you can see the logical plan and physical plan at the same time. And you can see it is just a very simple data loading and projection to extract the data that I want, because I have some transformations to load the WKB as geometry data. So now let's run the spatial drawing here. So it is basically just drawing the data set, and the condition is a spatial predicate. So that's why this is called spatial drawing, right? So I use contains to only preserve the coffee shops inside those counties. And in the result, I actually does a aggregation to count the number of coffee shops in each counties. So okay, let's do it. And it runs very quickly because the data set is small, and also there's order by. So it is a spatial drawing followed by a aggregation followed by global order by or global sorting. So you can see these are the results and the names of the county and the geometries and also the count of the number of coffee shops in each county. So that's spatial drawing. You can see that's pretty easy, just similar spatial SQL syntax as you have already did in Apache Sedona, but this is like a single host solution that is like much faster compared to you using Apache Spark, Apache Sedona on Spark on your local host. And then you can just also use the longboard, but here I use some more complicated code to color the counties according to the number of coffee shops. So you can see that if the color is darker, then there's no coffee shops. You can see this is the Los Angeles County, and apparently it has most of the coffee shops in California, and also here this is the like San Francisco. So the result looks pretty good and quite intuitive result. Okay, and and you can take a look at the query plan. So you can see here. Oh, let's see. So you can see here there's a sort and sort followed by an aggregation, and what's below the aggregation is actually a spatial drawing operator. So if you see this, then you know that we're actually using a optimized physical operator that is specially implemented for spatial drawing. And I will talk later about how it works and why it runs spatial drawing much faster than Apache Sedona on a local host. And if this looks quite cumbersome, this text representation of this query plan looks cumbersome, you can use format equals tree, and it will give you some nicer visualization of the query plan. So you can see it is quite like what DuckDB does. And you can see there are two arms of spatial drawing. and the result of spatial join was fed into an aggregation, and there's a local aggregation, a global aggregation, and also finally fed into a sort. So okay, this is a normal spatial join that you will normally write. So there are some other queries that will also be run as a spatial join. For instance, this decorrelated subquery as a query window. And so this looks like a range query. And the query window is retrieved by running a subquery, this one. But this query is also run as a spatial join. So you can see here, this is a spatial join, and this one on the left side is the index side. It is the subquery, and the right side is the coffee shop, the streaming side. And the reason why we run it as a spatial join rather than a kind of a decorrelated subquery is because we can do something clever by caching the query window geometries in so that we can reuse it instead of like parsing the geometries each time we inspect a row from the coffee shop. So there's some clever optimization we can do here, but it may still not be the most optimal way. For instance, we cannot do some like spatial predicate pushdown if the other side is read from a set of bunch of GeoParquet files. So we may still need to improve this. And these examples are using range joins, which means that the spatial predicate are like ST contains within intersect, and we also support distance join. So this is an example of distance join. So you can see the join condition can be ST d within, or if you like, you can also write something like ST distance A and B less than the distance. So these are equivalent. And in this example, I'd like to do an anti-join, which means that we want to filter out things that are not near the buildings that are not near hospitals, which are those buildings maybe lacking healthcare support. And so you can, as you can see, SedonaDB supports all sorts of like joins, not only inner joins. So you might have already know that the Apache Sedona for Spark only supports inner join out of box. And as a comparison, SedonaDB supports all kinds of joins, outer joins and semi joins and left anti-joins, etc. And so one of the reasons is that it is much easier to implement this kind of outer joins or anti-joins on a single host. And I will talk about this later. So, okay, now let's get back to how spatial join works. And I will explain why this single host implementation can be faster than a Spark-based implementation. And so this is how spatial join works. So actually, we are building a spatial index for one side of the joined data set. And we scan the other side, which is called the probe side. And for each batch in the probe side, we query the spatial index. So please know that the spatial index is actually a global index, which means that even though we have multiple partitions on the index side, and we can scan the index side in parallel, the three partitions, and we build one giant array index containing all the records in these multiple index partitions. And then we concurrently probe that index using these multiple probe partitions. So this probe may happen in parallel because this R3 index is immutable. It is immutable. So concurrently probing it does not incur any problems or risk conditions. And so this is how spatial join works in SedonaDB. And compared to other sorts of joins in data fusion, because you might know that SedonaDB actually is built based on data fusion, and data fusion is a volcano-based query engine, and it uses exchange operator, and it is called repartition exec in data fusion. And this is an example of how hash join runs in data fusion. So it is actually a partition-based or exchange-based parallelism, which means that the multiple index partitions have to be repartitioned by the join key. Now let's talk about the hash join. Now we can repartition by the join key with split the problem into several smaller pieces, and each of them is a self-contained problem. So we can just build each hash table for that small partition, and also we also need to repartition the probe side, and so that each partition will build its own smaller hash table. So this is how data fusion's hash join works. And compared to this, we build one single index for all the partitions, which means that the index is shared. This is different from the approach of the hash join operator. So why we are doing this? The main reason is that the spatial data cannot be partitioned cleanly. And if you take a look at how Apache Sedona partitions the spatial data, you may find that it has to duplicate some of the data that crosses multiple spatial partitions. And also we have to deal with the duplicates introduced by this partition data duplication. And for inner join, we can play a nice trick to remove the duplicates when producing the join results. But it makes it hard to correctly run outer joins, for instance, left outer joins. Because you duplicate data, it is hard to tell if a data on the index side actually hits nothing. And so that's why when we're implementing a single host query engine, we do not partition the data. So we just build one spatial index that is shared by all probe partitions. This is a bit of like the model-driven parallelism, where we also build a global index, but we implement this in a volcano-based query engine. And so this is actually one of the reasons why SedonaDB can fundamentally be faster than Apache Sedona and Spark, because Spark has to partition the spatial data, and the partition data has to be like written to disk as the map files. So Apache Sedona and Spark did this kind of spatial partition for horizontal scalability in the cluster setups, because it is hard for different nodes to talk with each other. So that's why we have to subdivide the problems into smaller pieces by spatial partitioning. But in a single host setup, we do not have this problem. We can get rid of all these hassles of partitioning the spatial data and just build one single index. So, okay. And that is when SedonaDB is faster, and there's still something we need to do about it. And so one thing that we have to work with larger than memory dataset. And as you have as we have shown here, we have a global arch index. Currently, this index is like in-memory index. We have not implemented any kind of splitting or partitioning for this index. So if you have if you want to join larger in-memory dataset, you may hit problems. And so there are several like approaches to deal with this. We may implement a splittable arch index, which means we can swipe in and out of those leaf pages into memory or out on disk. Or we can implement a spatial partitioning based approach. And if the data is just that large, it cannot fit into memory, then we may still need to partition it. Or we can implement a switch to an algorithm that has less memory footprint. For instance, plane sweeping is kind of like a sort merge join approach for spatial join. And currently, we also do not support geography predicates. And all these demos I have shown are working with geometries. And the complexities of supporting geography is we need to compute the equiboxes for geography objects. And this involves some tricky mathematics. It is much harder than just simply taking the mean and the max of all the coordinates in the geography. And we need to handle the bounding box wraparounds at the anti-meridian. Okay, so that's what we still need to improve on the spatial drawing of SedonaDB. Okay, so that's it.
Cool, great presentation, Christine. Now let's hand over to Feng. Feng going to talk about k-nearest neighbor join. Please, Feng.
Hello, everyone. My name is Feng. I'm the developer for SedonaDB, especially on the KN join and some of the distant metrics UDF functions. So for our first release. So I'm going to talk about the KN join today, specifically like how, why and how we implement that in SedonaDB. I think as Dewey and Christine has explained, the SedonaDB is actually a native single host query engine that's can handle spatial workload pretty efficiently. So KN join is one of the spatial join type that we have implemented in Sedona. Spark version of Sedona. The reason why we implement that is because we see a lot of use cases that people actually wants to have a very efficient way to find either the closest or the k closest neighbors for their geometries, right? For example, if people want, when people process the New York taxi location and building data set, they want to find the closest buildings for each taxi very efficiently, or they want to process data in batch, like area amounts to find if the location that the taxis are, is mostly optimized or not. So there are a lot of different use cases for KN, but we don't see very efficient implementations either in PostGIS or DuckDB or Spark. Can do these things very efficiently. It's why we decided maybe this is a good idea to implement that. So we first did that in Spark version of Sedona. I think last year. The challenge there is because very similar to what Christine has explained, right? You need to partition the spatial data very precisely, and that's usually a challenge for people working with distributed spatial analytics. And then you need to, once you have a partition, you need to have some kind of a spatial index specifically designed for spatial, like R-tree, quad tree, and those different kind of spatial indexing techniques need to kick in. So yeah, we did all of that, and then we see very efficiently performance on Spark version. So and then when we release SedonaDB, I think we want the KN join to be the first to be included in the first release, and then we did, as you can see here, very easy to do that. First, you can initialize the context here, the same way that you will do with other kind of load. So in order to do the KN join, you need two tables. One table is query query side, which means you want to find for which of the data set you will find the nearest neighbors. Now, so I'm demo here is I create a few cities with their location. You can see here. So and then the second table is the object table. It's the it's the locations that you want to find the neighbors within. Like here, I'm creating some of the POIs, some of data here. You can print them. And then once you have these tables, you have geometry columns defined in both tables. Then you can use this very concepts can join syntax to basically do it. It is exactly the same as the open source Sedona. I mean, the Sparkle version Sedona, you can basically use the exact same SQL there and here. So the really all other things are the same. The only things that instead of using a spatial predicate, you can use STKN here with a few parameters. So here you define the query side, here you define the object side, and then here's the K, like how many neighbors you want to find. And then do you want to use spheroid distance or not? So we basically support different type of distance metrics here. And then you can run this as you can see. You can display the query plan. All the others are very similar to spatial join. As you can see, we actually reuse the spatial join execution in here for these two tables. It's not. This is why our spatial join is getting efficient, because we don't actually use data fusion's default, like hash join or nested loop join type. So we have our specific type of execution implemented for the spatial join or k-n join here. K-n join is the same. You can also display more details in here. Like you can see here, we have this execution types inner join, and we're using STN k-n operators for that. So this is the way that you can check, the exact physical plan for your query, and you can also run the query by yourself. Yeah, you can see for each of the cities, it will find the 3 POIs for them. This is like very, I mean, the simplest way that you can run this with the SQL. Of course, you can visualize either on a map or on a plot with that. I do have some others. I don't see them here. Okay. So so other things I want to mention is a barrier function. So when, like for example, you can see a join like this, right? So a lot of times, like people want to apply a regular filters with the k-n join, which means, for example, you want to find the nearest restaurants instead of all different kind of POIs, right, around a city or a certain location. Then people can combine different join conditions for that. With the regular join, basically the query optimizers can optimize the the order that you want to add as a join or as a join condition. But with the k-n join, because the left side and the right side cannot be exchanged, so you cannot do that. So that you need some way to control whether you want to do a regular join first or a k-n join first, right? So we introduced this barrier function to do that. So basically, the barrier function is a query optimizer barrier that can control whether you want to apply this as a join condition or actually want this as a join. So for example, here, because I'm applying a barrier function, this query will do can join first and then apply those conditions after the join. I mean, if you don't want to do that, then you can remove the barrier function and then you can do a regular join and then get a result and then apply the can join. So that's a special thing we introduced here to control the join order. We also did the same thing with the open source Sedona Spark version. You have the same barrier function that you can use to control, and also you can use a query hint in there as well. So that's the barrier function, and then here I want to show like so we picked the PostGIS and DuckDB to see like how they can join, right? They don't have the specific join type in their execution supported natively, but because they have a spatial distance function, you can also do can join with some kind of like a bit complex SQL. For example, here's the PostGIS. It uses a special like nearest neighbor operator, and then you can combine that with a window function, and then order that by the distance you calculate there. I mean, basically, this is the PostGIS, but it does the same thing as our can join, and also the DuckDB. DuckDB doesn't have this operator, so you have to calculate distance, the pairwise distance one by one, and then rank the distance, and then pick the top k from there. This is why like I don't think they are as efficient as us. And I also want to show so in the code base, if you go to our SedonaDB code base, and then under the root, there's a benchmark folder that you can basically find some of our end-to-end benchmarks. So the can join also has one here. So you can see. So I'm going to run this can join with with 3 different engines I just mentioned. And then you will get a very nice report like at the end showing how they compare to each other, right? Yeah, let's just give a few more. I think it will finish in maybe like 60 seconds. So basically, what we benchmarking here is for different k. So we have k equal to 1, 5, and 10, I guess. And then we have a small data set, we have a large data set, and then we run them. We run the same we run the same can join with 3 different query engines, SedonaDB, DuckDB, and PostGIS. And here we'll see the results very soon. Okay, just give that a few more seconds. And by the way, you can run this command with the same similar command, but with other like this is the distance join, this is the UDF functions, overlay functions, different predicates. You can run the same thing in there. So as you can see here, this is k equals to n, k equals to 10, k equals to 5, and then for small data set, large data set for different engine. As you can see, because we have the specific join type in our engine natively, SedonaDB is much efficient than all the other like query engines in terms of the same join. Yeah, so that's something I think you can run on your machine very, very easily if you just clone the repository and then run them locally. But yeah, so I think that's let me see what I have. Oh, so we also did so on the spatial bench that Gia mentioned early on. So the last join is can join. So we also did a lot of comparison, and then we found, compared to the other two engines, our SedonaDB is much efficient. I mean, you can also take a look if you are interested in that. Cool. I think that's what I want to cover. Thanks, Jia.
Great. Thank you, Feng. Let's move on to Pranav. Talk about the data generator of SpatialBench.
Yeah, thanks, Shia. Yeah, so I'd like to briefly talk about the data generation and the data distributions that SpatialBench offers. Before that, I'd like to briefly touch on the design of the data model for SpatialBench. It consists of a total of 6 tables, the trip table being the fact table, and the remaining tables are dimension tables. It consists of 3 spatial tables, which means the trip table, building, and zone tables have geometry columns. The ones highlighted in red are those. So pick up, drop off locations, which are points, and buildings and zones have a boundary field, which are polygons. And the great thing is they scale up with a scale factor, and they are highly reproducible. So particularly like the trip, customer, driver, vehicle, they all scale linearly. So they scale with the scale factor. The building, however, scales in a log, on a log scale. And the zone table is a special table. For the zone table, the SpatialBench data generator is utilizing real-world data sets, namely the Overture division area dataset. And the scaling of it is tiered, it is staggered. So it produces 156K approximately rows for scale factors between 0 and 10. And then it keeps adding like additional subtypes as the scale factor increases. And this is to kind of follow the complexity that each of these subtypes offer. So neighborhoods, zones are going to be slightly more complex than microhood, macrohood, and county. And the complexity of it is based on like the number of nodes those particular geometries have, and also the area that they cover. So these, the higher complexity ones, like the country one, it can have like millions of nodes in a single polygon and can obviously span like an entire country. Cool. So let's get into the tool that SpatialBench offers to actually generate these datasets. A few key features about the data generator. First of all, it inherits all of its performance from the TPCH Gen RS project, which is a really interesting project. It's written in Rust to generate TPCH data, and it's super fast. So it inherits cool things like the multi-threaded generation and the streaming, and uses like a constant memory. So you can really go up in scale factors and generate a lot of data, like upwards of 1,000 scale factors. Other notable features are SpatialBench data generator offers like a lot of different spatial distributions for those spatial tables. And we'll get into those in the later slides. But it also offers like super precise geometries. Especially, this matters especially when you want to scale up, like maybe to 1,000 scale factor or above. That's when you want to avoid collisions between points and geometries. So Spatial Bench DataGen provides like the highest precision of geometries, which is 10 raised to 9, which is like sub-millimeter precision. And another cool feature of Spatial Bench is that it's highly configurable. So you can tune the data distributions, the outputs, the row groups. There's a lot of things that you can explore when generating all these tables. Okay, so these are like some examples of how to use the Spatial Bench CLI. These are some that I really like and are really awesome. The first one is just a simple way of generating Parquet files for all those Spatial Bench tables at scale factor 1. The second one gives you configurability about the row group size. So by default, Spatial Bench is going to use 128 MBs as the row group size. And that is, of course, configurable. This can, by the way, impact how well certain scan operations run on these tables. Another thing is that it can offer like partitioned outputs. So you can create like multiple Parquet files for the same table. That is done via the parts and part CLI options. And yeah, so like it also offers configuring the spatial distribution. So you can kind of control what kind of distribution you want and bring in certain types of skews to like test your engine in different scenarios. So all that is done via the Spatial Bench config YAML file. You can find that in the root repository, like a root directory of the repository. Okay, so let's get into like the spatial distributions that Spatial Bench offers. So it offers 7 today, and of course this can be extended to more. If you're interested, please reach out. We can work on that. Yeah, so those are like the uniform, diagonal, Gaussian, Sierpinski, and bit Thomas, and an extension of Thomas, which is the hierarchical Thomas. The first 5 are taken from the Spider generator, the Spider spatial generator. They have really cool algorithms for these 5 distribution types. And the Thomas comes from a point process theory. We can get into more details later. Okay, so the way the data gets placed on the actual planar map is that we use something called continent-bounded affines or affines. What that means is it's trying to restrict all the geometries that get generated onto the land masses and the major land masses where generally a lot of settlements are there. So what it ensures is not a lot of geometries fall into like the middle of the ocean. And then it becomes unrealistic and also doesn't follow like the natural skew that continents offer. So that's what we try to, that's the kind of order or the predictability we try to bring into the random spatial data generation part. Yeah. Okay, so I'll like quickly walk through the different distributions. First one is the uniform one. It is pretty evenly spread out. It's like a good baseline. It does not offer a lot of skew, spatial skew, but it's definitely a bit unrealistic. But it's a good starting point to test a particular engine. The next one is the normal distribution or the Gaussian distribution. It is essentially just one single cluster, and then there is like points, decaying points around that parent cluster that is controlled by the standard deviation parameter. Also offers a little bit of skew, but not too much. Another interesting one is the diagonal distribution. This one spans across a diagonal, and what it's good at is like, it is like pretty predictable, but it's good at stressing engines that use, axis-based partitioning, and that's when the skew actually occurs. But most of the engines are good at handling that as well. Next one is a funny looking distribution, the Sierpinski distribution. It follows some like fractal, and it looks like triangles nested within triangles. It's decently skewed though, so it's useful for testing engines for sure. Another one is the bit distribution. Also comes from the Spider spatial distribution suite. So it produces these pockets and clusters, and some clusters are dense, some are not. But this is also fairly predictable, and there is a fixed pattern to it. Okay, so the Thomas distribution is something that is getting somewhat near how real world data is actually spread out in the real world. So this is a Gaussian variant of the Neyman-Scott point process. And what it does is it springs out these parents. Parents meaning you can think of it as a centroid of all these different clusters. And then it disperses these offsprings around the parent. And those are controlled by, like, I think it's a Pareto distribution. So it's the skew of which you can control based on certain parameters there. Certain parameters meaning like you can control how many parents get generated, what the mean offspring can be, like the sigma of the spread of each cluster, things like that. The last one is the hierarchical Thomas distribution. This is just an extension of the Thomas or the Gaussian Neyman-Scott process. What this means is it's just doing a two-tiered Thomas process because the Thomas process is a, it's like, it makes sense when you want to mimic certain activities, but the way settlements and human activity is prevalent in the world, it follows like cities, and then there are like sub-clusters within the cities. So that's when the hierarchical Thomas can be useful to mimic. So it does a multi-level clustering. So there are like cities, and then there are neighborhoods within the cities that may have more dense activity within them. So this is the one that SpatialBench uses by default today. And it generates data that looks something like this. Let me quickly, I think I have it open here. So I can show you how this actually looks like. Some of these clusters are super dense, and then you can see how these points are dispersed out. Yep. Okay. Yeah, this is another interesting thing that SpatialBench incorporates, is that For the trip table particularly, it mimics the New York City's taxi cab dataset. And we wanted to make the trip table very similar to that because first of all, New York taxi trip is a real world dataset and it provides very realistic trip data. So things like trip distances are extremely skewed. You can see in the graph, it's the y-axis is log normalized, but you can see like there's immense skew in the data. Some trips are really long, some trips are very short. So especially useful for modeling like distance-based queries. And we wanted to bring that same characteristic into the trip data. So we use something called kernel density estimation to mimic the exact spread of the trip distances. So mind you, this is just the trip distance. So the distance between the pickup and the drop-off point is what we are controlling here. And it gives us very realistic looking trip distances. Yeah, that's all I have. Thank you.
Thank you, Pranab. Let's move on to James. James, you are muted, please.
All right. I've been muted a lot recently. So I worked a lot on the execution of these queries. Gia had a big part in writing them. I helped with that as well, and then rewriting them into various queries. There's a lot of, actually, we'll get into that in a minute. So I have a couple quotes here. First is from George Box. This is pretty famous. All models are wrong, but some are useful. Similarly, like all benchmarks don't apply to your use case, but some of them might be helpful. And then another one I have here is there's no cheating in climbing, only lying. The same thing is true about benchmarking. If you're forthright about what you've done in the benchmark, there's nothing, disingenuous about what you've done as long as you're forthcoming. So with that being said, we had a few tenets for the design of how we ran these queries. This is not to say these were our tenets for the design of the queries themselves, but how I tried to execute these queries across different engines. So in spatial SQL, things are not as standardized as other parts of the SQL standard. So in something like TPCH or TPCDS, you often can run all of the queries with exactly the same syntax on all the different engines you're targeting. But I found that with SpatialBench, that wasn't always the case. Another thing was using partitioned files in an object store. Specifically, those were in S3 and they were Parquet files. So this meant at scale factor 1000 rather than having, I think it's a 250 gigabyte trips file in a single Parquet. We would break that up into very roughly 256 megabyte files. This was driven by kind of what is normal as a Spark user to have many Parquet files of a medium size or a smaller size rather than single very large Parquet files. We were trying to measure the cold start performance. So a lot of engines like DuckDB will cache pieces of data that you've used. And so the second query performance will differ significantly from the first if you have those kind of caching functionalities enabled. We decided that we weren't aiming to test that behavior. And then finally, we wanted to minimize or to the greatest extent possible, eliminate writer or serialization costs. There might be, you might feel that, reading the data from S3, but then not incurring that overhead to read it over the network, but not writing it out to disk or to network might be like incongruent. I felt like this was the right way to go because you always have to read your data in a production environment. Your data is almost never already on the host because the host is likely an ephemeral cloud environment, whereas you don't always have to write your data. What is downstream of any given query can change based on like your use case. So in terms of like what we tried to accomplish with these queries, and like Gia, feel free, or anyone else feel free to like chime in if you disagree or have something you want to clarify on here. We're trying to reflect common analytical spatial queries. So these are, kind of your standard types of queries in an analytical benchmark: joins, aggregations, group bys, orderings. But they have spatial predicates and spatial functions in them. We're trying to test the optimization and the execution layers of these engines. So some of these queries, if you have a good query plan, you would expect them to have maybe marginal difference in performance, but selecting the correct query plan might be challenging for one engine if it's missing some kind of optimization, and vice versa. Picking the optimal query plan might be the easy part, but having a physical execution layer that does that action efficiently may be challenging for some of them. Another choice we made here, or at least we've made so far, is that all the distance operations and all the spatial relationship operators are performed on a Cartesian grid. So there's no sphere or spheroidal modeling of the Earth when we calculate how far apart two things are. And then finally, we prefer ANSI compatible SQL to anything that is engine specific. So if it can be expressed with an ANSI compatible operation, we pick that. And we built these Spark and Sedona first. And when I say Sedona, I mean Sedona Spark, because that existed at the time that we were building these. We work with Apache Sedona every day. It's what we're familiar with, so that was kind of the starting point for writing the query itself. This is not like massively impactful, I think, to the outcomes. It just informs how you'll see like the code to generate the queries is structured for the different engines that we support today, and like, may expand in the future. So in terms of actually executing these, we tried to disable any caching functionalities we were aware of. We collected results when possible. And here I'm talking about the results that we posted on the Sedona blog. So this is like SedonaDB, DuckDB, and GeoPandas. I didn't run Sedona Spark or any other engines you could think of with these kinds of bullet points being applicable. So we collected the results when it was possible. I believe that this was for all queries except query 12, which is the KNN join. And then for the KNN join, we call count. And Pranav, correct me if I'm screwing anything up here. Because the KNN join returns a very, very large number of results, which was causing all engines to go out of memory on that query. A feature from Spark. I've run these queries against Spark, and Spark has this feature that I'm quite fond of called the no-op writer, where each task in the stage that is writing the data out, it like writes the data out by just like generating the data for it and then, writing it to null, like putting it nowhere in particular. So I don't know. Tui might disagree with this, but as far as I know, DuckDB, SedonaDB, they don't have anything like this. GeoPandas kind of does because it is an eager engine, so it like the data frame itself like exists. The data is materialized in it, so in some sense, it's already equivalent to a no operator. We averaged out 3 runs for each of these. And we had an M7i 2X large host, which is an Intel processor, 8 cores, 32 gigs of RAM. And I want to say when we did those runs, so we were running, each query 3 times. It's on the same host for all those executions, and it is in the same process. So we don't like start a new instance of like Python to run each query or anything like that. So if you run it differently, maybe you'll find something different that could be interesting. So as a comparison, I have query 12 here. This is the one that varies most drastically between SedonaDB and DuckDB. So this is that KNN syntax that Feng was talking about earlier. Whereas in DuckDB, we have a cross-join lateral. I would say that DuckDB doesn't have any like special optimization or physical execution tricks for doing a KNN join. It doesn't support any kind of syntax, so we had to use this, which I would call like vanilla Spark, although you do have to evaluate these spatial functions to get the inner table in the cross join lateral. And then finally, I kind of am picturing GeoPandas here. This is just, this goes way off the end of the page. I implemented basically a nested loop join in Pandas, Python. I forget exactly what I wrote here. It's in the repo if you want to check it out. But Pandas, similarly to DuckDB, doesn't have any built-in KNN join support, so we kind of had to roll our own thing. And rather than doing like a Cartesian product and then filtering, I gave it a little bit of an effort to optimize this. Although in general with the GeoPandas code, I didn't make any effort really to optimize it because I felt it was unfair to the other engines that have implemented a query optimization layer. So other things, some of these I have done, others I haven't done, but these are other engines that, because of their nature, I think were harder to create an apples to apples comparison. And, not the benchmark doesn't have to be perfectly apples to apples to be useful, but, just for now, for this initial release, we kind of sidestepped these questions, and we're happy to like see people run these benchmarks against these platforms or in various other configurations. First is GeoPandas. It's not SQL. There's no query optimizer. So first off, I had to rewrite all of the queries like from the ground up. And second off, there's all these choices you have to make about how much do you want to optimize this, which optimizations are fair, which optimizations are applicable to whatever you're trying to use the benchmark for, I suppose, is ultimately the question. Postgres, PostGIS, Microsoft SQL, MySQL, etc. Any of these like more traditional RDBMSs, these have their like proprietary table format. You need to like ingest the data into the table before you run queries on them. I know that's probably not like strictly true. They have some concept of an external table or whatever. And then you have these stateful indices, where SedonaDB, DuckDB, Sedona Spark would likely spool the index inside of the query execution. You can obviously do all these things, create tables, create indices, and run these benchmarks in these traditional systems. but it's a different methodology. Your measurements should probably be distinct. And then there's also, Spark and the whole suite of Spark compatible engines from various SaaS providers. Yeah, I think we're probably all familiar with Spark here. You can totally run all these queries in Spark. But when you have the cluster, it begs all these questions of like how your cluster's put together that I didn't want to wade into. At least not for this initial release or for the open source release. So I'm kind of sidestepping the whole question of running it in the various Spark compatible interfaces that Apache and software vendors offer. And then for future work, I think I have this twice. Yeah, okay. For future work, that you can always run more engines. We're targeting raster queries at some point in the future. I forgot the bullet point here, but we're also thinking about like using geometry types to kind of run the same exact queries on the same data, but using geometry rather than, am I saying it wrong? Geography instead of geometry. And then is there anything else that we're missing with these benchmarks? That's something I'd love to see from the audience or you guys in Discord or whatever. All right. Thanks, guys.
All right. Thank you, James. I know we are running out of time, right? So, let me just wrap up the office hour today, right? So as you know, Sedona is always calling for help, right? So you can contribute to Sedona and SedonaDB by going to our GitHub repository, right? Look at the GitHub issues we have. So there are lots of bugs and issues you can fix. You can also join our Discord channel. I posted the link in the chat, so please feel free to join us. And if you have anything you want to share with the community, we oftentimes have live stream about Sedona success story. So if you're interested, please reach out to me through my email and also our Discord. All right, great. So that's all for today. Thanks for everyone for joining the office hour today, and we'll see you next month.